In this lecture, let us remind ourselves of few of the basic properties of the Yang-Mills gauge theories, right? So we are interested in this because we know that gauge field, the gauge field mediates forces between matter fields, and it couples them to the currents of the corresponding global symmetry, right? So it couples them to the currents of the uh, global symmetry. Right. Now, from previous lecture, we know that the energy momentum tensor is the natural source of gravity, right? So we have developed or established this fact that this thing is a source of gravity, or it's a natural source of gravity. Then it is attempting to construct gravity as a gauge field that results from gauging the global symmetry that the energy momentum tensor corresponds to. So we are going to firstly consider two cases, and they are, first we'll talk about the abelian gauge theories, or abelian case, and for that we'll consider a theory that is invariant under some global symmetry group. And for that, we can just use the theory of a massive Dirac field, and let's call it psi, with a Lagrangian that is equal to psi bar iota d slash minus m psi, right? Now we know that the Dirac Lagrangian is globally invariant, so it's globally invariant under the U1 group or U1 transformations, right? So mathematically, I would write that as psi goes to exponential negative iota times theta psi, where this theta is a constant, right? Now, if we apply Noether's theorem to this, then we get the conserved current. So after applying Noether's theorem, we get a current that is conserved, which is JA is equal to psi bar gamma A psi, right? And the fact that it's conserved can be written as partial A JA is equal to 0, or the derivative of the current vanishes. And we can also write the charge Q as the integral d3x of J naught. Right. So this is just from a basic quantum field theory, or right. So now note that even though invariant under global transformation, this Dirac Lagrangian is not invariant under some local transformations. But we can do that. We can make it invariant by simply introducing some new field. Let's call that field A mu, or I might change this mu to A, so let's just call it AA, right? And we'll define this field to make it locally invariant, right? Now, to picture this is the starting point for QED, right? So when we want to develop a quantum electrodynamics QED theory, we introduce this field A to make the Lagrangian invariant locally. Now this new field is called a gauge field. And it would turn out that we are pretty familiar with this field, or at least they are who have studied electrodynamics, right, or electricity and magnetism. And so with this, then we can rewrite the Lagrangian as L is equal to psi bar. That's a very funny psi, but yeah, iota capital D slash minus m psi. Now this capital D slash, or this capital D, is defined as your dA partial A plus iota E, where this E is the electric charge, times this field AA. And this is called a covariant derivative, right? So you have defined your derivative, or redefined your derivative, in terms of this new field A, or the gauge field. Now, to ensure the invariance of this new Lagrangian under this U1 group, the covariant derivative of the field, which is this thing dA of the field, so dA psi, it is obliged to transform as this thing, exponential negative iota theta, which is a function of x this time and not a constant, times this covariant derivative of the field dA psi. Then this implies that the gauge fields should also transform as this thing, which is A transforms as A plus 1 over E, where E is again the electric charge, times partial A times theta of x, right? Okay, now so far our gauge field is stationary, or it is not allowed to propagate, right, in space. So the next step is to make the gauge field dynamical, right, so that it can propagate. And so for this, then we have to introduce a kinetic term for this field A, and this can be done with a bilinear connection of the field strength tensor, that is minus 1/4 F AB times F AB, right? So we need this. This is also known as a bilinear connection. And why do we need it? Well, we need it to make the field dynamical, so that it is allowed to propagate through space-time, right? And we know that we already know that this FAB, it is defined through a relation of this thing, the covariant derivatives. The commutator of dA and some dB is equal to iota E, where E is again the electric charge, times partial A AB minus partial B AA. And this thing is simply equal to what? Well, because we know that this thing is equal to, you know this from your course on electrodynamics, this thing is simply equal to FAB. But it turns out that this is how you define this FAB. This commutator is used to define FAB like this. And so I can write this as FAB. So this is the pure definition of your field strength tensor, right? So yeah, I thought I would mention this over here. Now note that this term that I wrote, the bilinear connection, which is minus 1/4 FAB times FAB, this thing is a positive definite matrix from your linear algebra. You should recognize that. And it is locally invariant, under this U1 group. So after all of this, the modified Lagrangian can be written as minus 1/4 FAB times FAB plus psi bar times iota t slash minus m psi. So yeah, wonderful. Now, if you look at this Lagrangian, you'll immediately see that the coupling of the gauge field AA to fermions takes, so if I couple this to fermions, it takes the form of JA, A. And so if I look at this current JA, it would be psi, which is psi bar gamma A psi. This current, we can tell from this Lagrangian that this current is actually acting as the source of the field that we have, the gauge field, right? Now with this in hand, we have everything we need for the abelian case, so we can move on to the case number 2, or non-abelian case, right? Okay, so for a non-abelian example, let's use a theory whose symmetry group is a non-abelian one, right? So for that we can just consider a field psi, that transforms in a fundamental representation of some compact group. Let's take that group for our purpose SUN, right? And so the transformation can then be written as this unitary operator psi. Now with this, u is equal to exponential iota w w naught plus 1 by 2 w alpha lambda alpha. Now these lambda alphas are simply the generators of the SUN group, right? So of SUN, right? Now these generators obey a commutator relation, which is simply lambda alpha over 2 comma lambda alpha over 2 is equal to iota the structure constants f alpha beta gamma times, the structure constants are the structure constants of the group, right, times f gamma over 2. And also there is this relation, that is the trace of this thing, lambda alpha over 2 comma lambda beta over 2. Actually I should have used beta over here as well, so yeah, in this above commutator. So yeah, and this trace of this thing is simply equal to 1 by 2 times delta alpha beta, right? So just some useful relations that these generators of the SUN group obeys. You can get these from your course on group theory as well. Now the Lagrangian that we have or that we had was this one, psi bar iota partial, or calling it just d slash minus m psi. This thing is invariant under these SUN transformations, right? So under these transformations with u is this thing. So as long as this w naught, this thing w naught w alpha, they are constants, then this implies that this Lagrangian would remain invariant under the SUN transformations. Beautiful. Now to promote its invariance to a local transformation, that is psi transforms as u, which is a function of x, times psi, we have to introduce the gauge fields, that is a, so not just one, but we need more than one, and we need covariant derivative dA, right? So we need this to promote the invariance to local transformation, right? Okay, so for that we have dA is equal to partial A plus iota G lambda alpha over 2 A alpha A, which is or it is equivalent to having partial A plus iota G G this thing. Now this A, I'll just call it a cursive A, right, is different than this A, right? So these two are different A's. Now how is it different? Well, it's just the fact that I am using the matrix notation in which this cursive A is equal to lambda alpha over 2 times your regular A in alpha, right? So now the transformation properties for this thing are simply dA psi is transformed as u of x times dA psi, and your this cursive A is transformed as u times cursive A u inverse, right? Plus, of course, this term iota over G partial A of u and u inverse. And finally, this dA alone itself is transformed as u dA u inverse. Now again, the dynamics of the field is given by this field strength tensor that we know F alpha AB, and or we can define this F alpha AB in a matrix notation as well, because we have defined this field in the matrix notation. So let's just go ahead and do this. Let's just find a matrix notation for this. Well, not fine, I'm just going to write it down over here. So, well, that is the commutator of dA and dB, because remember the strength tensor is defined through this relation of the commutator of the covariant derivatives, and this is equal, this would be equal to iota G F A B, which is equal to having iota G lambda alpha over 2 times F alpha AB, right? Okay, so yeah, so now from this I can write down the explicit expressions for this cursive F and the original F, which would be that now this F is defined for a locally invariance of the non-abelian gauge theory. This is defined as partial A cursive A B minus partial B cursive A plus you will have some extra term that is G times the commutator of cursive A and cursive A B. And we can have this normal F A B, which would be equal to, well, there would be an alpha over here as well, which is equal to partial A, your normal A this time, right, alpha B minus partial B A alpha A minus the extra term would be with the structure constants this time, as we're not using the matrix notation for this expression, which would be just simply this thing over here, right, A beta A gamma B. So this was just a revision for your Yang-Mills theory, and in the or next time we would just do all of this thing for the case of gravity, right? So we would be developing what we know for Yang-Mills theory. We would be developing that for the theory of gravity.